Chapter 4 Performance Testing Tasks 4.1 Planning 4.1.1 Deriving Performance Test Objectives. Stakeholders may include users and people with a business or technical background. They may have different objectives relating to performance testing. Stakeholders set the objectives, the terminology to be used, and the criteria for determining whether the objective has been achieved. Objectives for performance tests relate back to these different types of stakeholders. It is a good practice to distinguish between user-based and technical objectives. User-based objectives focus primarily on end-user satisfaction and business goals. Generally, users are less concerned about feature types or how a product gets delivered. They just want to be able to do what they need to do. Technical objectives, on the other hand, focus on operational aspects and providing answers to questions regarding a system's ability to scale or under what conditions degraded performance may become apparent. Key objectives of performance testing include identifying potential risks, finding opportunities for improvement, and identifying necessary changes. When gathering information from the various stakeholders, the following questions should be answered. What transactions will be executed in the performance test and what average response time is expected? What system metrics are to be captured, e.g., memory usage, network throughput, and what values are expected? What performance improvements are expected from these tests compared to previous test cycles? 4.1.2 The Performance Test Plan. The Performance Test Plan, PTP, is a document created prior to any performance testing occurring. The PTP should be referred to by the test plan. See ISTQB Foundation Level Syllabus, which also includes relevant scheduling information. It continues to be updated once performance testing begins. The following information should be supplied in a PTP. Objective. The PTP objective describes the goals, strategies, and methods for the performance test. It enables a quantifiable answer to the central question of the adequacy and the readiness of the system to perform under load. Test objectives. Overall test objectives for performance efficiency to be achieved by the system under test (SUT) are listed for each type of stakeholder. See section 4.1.1. System Overview. A brief description of the SUT will provide the context for the measurement of the performance test parameters. The overview should include a high-level description of the functionality being tested under load. Types of performance testing to be conducted. The types of performance testing to be conducted are listed. See section 1.2 along with a description of the purpose of each type. Acceptance criteria. Performance testing is intended to determine the responsiveness, throughput, reliability, and/or scalability of the system under a given workload. In general, response time is a user concern, throughput is a business concern, and resource utilization is a system concern. Acceptance criteria should be set for all relevant measures and related back to the following as applicable. Overall performance test objectives. Service level agreements (SLAs). Baseline values. A baseline is a set of metrics used to compare current and previously achieved performance measurements. This enables particular performance improvements to be demonstrated and/or the achievement of test acceptance criteria to be confirmed. It may be necessary to first create the baseline using sanitized data from a database, where possible. Test data. Test data includes a broad range of data that needs to be specified for a performance test. This data can include the following. User account data, e.g., user accounts available for simultaneous login. User input data, e.g., the data a user would enter into the application in order to perform a business process. Database, e.g., the pre-populated database that is populated with data for use in testing. The test data creation process should address the following aspects: data extraction from production data, importing data into the SUT, creation of new data, creation of backups that can be used to restore the data when new cycles of testing are performed. Data masking or anonymizing. This practice is used on production data that contains personally identifiable information and is mandatory under General Data Protection Regulations, GDPR. However, in performance testing, data masking adds risk to the performance test, as it may not have the same data characteristics as seen in real-world use. System configuration. The system configuration section of the PTB includes the following technical information: a description of the specific system architecture, including servers, e.g., web database, load balancer, definition of multiple tiers, specific details of computing hardware, e.g., CPU cores, RAM, solid-state disks, SSD, hard drive disks, HDD, including versions, specific details of software, e.g., applications, operating systems, databases, services used to support the enterprise, including versions, external systems that operates with the SUT and their configuration and versions, e.g., e-commerce system with integration to NetSuite, SUT build or version identifier. Test environment. The test environment is often a separate environment that mimics production but at a smaller scale. This section of the PTB should include how the results from the performance testing will be extrapolated to apply to the larger production environment. With some systems, the production environment becomes the only viable option for testing. But in this case, the specific risks of this type of testing must be discussed. Testing tools sometimes reside outside the test environment itself and may require special access rights in order to interact with the system components. This is a consideration for the test environment and configuration. Performance tests may also be conducted with a component part of the system that is capable of operating without other components. This is often cheaper than testing with the whole system and can be conducted as soon as the component is developed. Test tools. This section includes a description of which test tools and versions will be used in scripting, executing, and monitoring the performance test. See Chapter 5. This list normally includes tools used to simulate user transactions, tools to provide load from multiple points within the system architecture, points of presence, tools to monitor system performance, including those described above under system configuration. Profiles. Operational profiles provide a repeatable step-by-step flow through the application for a particular usage of the system. Aggregating these operational profiles results in a load profile commonly referred to as a scenario. See section 4.2.3 for more information on profiles. Relevant metrics. A large number of measurements and metrics can be collected during a performance test execution. See Chapter 2. However, taking too many measurements can make analysis difficult as well as negatively impact the application's actual performance. For these reasons, it is important to identify the measurements and metrics that are most relevant to accomplish the objectives of the performance test. The following table, explained in more detail in section 4.4, shows a typical set of metrics for performance testing and monitoring. Test objectives for performance should be defined for these metrics, where required, for the project. The table name is Performance Metrics. The left column is Type, the right column is Metric, as follows. Type, Virtual User Status. Metric, Passed or Failed. Transaction response time. Minimum, maximum, average 90% percentile. Transactions per second, passed per second, failed per second, total per second. Hits, e.g., on database or web server. Hits per second, minimum, maximum, average, total. Throughput, bits per second, minimum, maximum, average, total. HTTP responses per second, responses per second, minimum, maximum, average, total. Response by HTTP response codes. CPU usage, percentage of available CPU used. Memory usage, percentage of available memory used. Risks. Risks can include areas not measured as part of the performance testing, as well as limitations to the performance testing, e.g., external interfaces that cannot be simulated, insufficient load, inability to monitor servers. Limitations of the test environment may also produce risks, e.g., insufficient data, scaled-down environment. See Section 3.2 and 3.3 for more risk types. 4.1.3 Communicating about performance testing. The tester must be capable of communicating to all stakeholders the rationale behind the performance testing approach and the activities to be undertaken, as detailed in the performance test plan. The subjects to be addressed in this communication may vary considerably between stakeholders, depending on whether they have a business or user-facing interest or a more technology or operations-facing focus. Stakeholders with a business focus. The following factors should be considered when communicating with stakeholders with a business focus. Stakeholders with a business focus are less interested in the distinctions between functional and non-functional quality characteristics. Technical issues concerning tooling, scripting, and load generation are generally of secondary interest. The connection between product risks and performance test objectives must be clearly stated. Stakeholders must be made aware of the balance between the cost of planned performance tests and how representative the performance testing results will be, compared to production conditions. The repeatability of planned performance tests must be communicated. Will the test be difficult to repeat, or can it be repeated with a minimum of effort? Project risks must be communicated. These include constraints and dependencies concerning the setup of the tests, infrastructure requirements, e.g., hardware, tools, data, bandwidth, test environment, resources, and dependencies on key staff. The high-level activities must be communicated. See Section 4.2 and 4.3, together with a broad plan containing costs, time schedule, and milestones. Stakeholders with a technology focus. The following factors must be considered when communicating with stakeholders with a technology focus. The planned approach to generating required load profiles must be explained and the expected involvement of technical stakeholders made clear. Detailed steps in the setup and execution of the performance test must be explained to show the relation of the testing to the architectural risks. Steps required to make performance tests repeatable must be communicated. These may include organizational aspects, e.g., participation of key staff, as well as technical issues. Where test environments are to be shared, the scheduling of performance tests must be communicated to ensure the test results will not be adversely impacted. Mitigations of the potential impact on actual users if performance testing needs to be executed in the production environment must be communicated and accepted. Technical stakeholders must be clear about their tasks and when they are scheduled. 4.2 Analysis, Design, and Implementation. 4.2.1 Typical Communication Protocols. Communication protocols define a set of communications rules between computers and systems. Designing tests properly to target specific parts of the system requires understanding protocols. Communication protocols are often described by the Open Systems Interconnection OSI model layers. See ISO IEC 74981. Although some protocols may fall outside of this model. For performance testing, protocols from Layer 5, section layer, to Layer 7, application layer, are most commonly used for performance testing. Common protocols include database, ODBC, JDBC, other vendor-specific protocols, web, HTTP, HTTPS, HTML, web service, SOAP, REST, SOAP, REST. Generally speaking, the level of the OSI layer, which is most in focus in performance testing, relates to the level of the architecture being tested. When testing some low-level embedded architecture, for example, the lower numbered layers of the OSI model will be mostly in focus. Additional protocols used in performance testing include network, DNS, FTP, IMAP, LDAP, POP3, SMTP, Windows sockets, Cobra, mobile, true client, SMP, MMS, remote access, Citrix, ICA, RTE, SOA, MQ series, JSON, WSCL. It is important to understand the overall system architecture because performance tests can be executed on an individual system component, e.g., web server, database server, or on a whole system via end-to-end testing. Traditional two-tier applications built with a client-server model specify the client as the GUI and primary user interface, and the server as the backend database. These applications require the use of a protocol such as ODBC to access the database. With the evolution of web-based applications, the multi-tiered architectures, many servers are involved in processing information that is ultimately rendered to the user's browser. Depending on the part of the system that is targeted for testing, an understanding is required for the appropriate protocol to be used. Therefore, if the need is to perform end-to-end testing emulating user activity from the browser, a web protocol such as HTTP or HTTPS will be employed. In this way, interaction with the GUI can be bypassed and the tests can focus on the communication and activities of the back-end servers. 4.2.2 Transactions. Transactions describe the set of activities performed by a system from the point of initiation to when one or more processes, requests, operations, or operational processes have been completed. The response time of transactions can be measured for the purpose of evaluating system performance. During a performance test, these measurements are used to identify any components that require correction or optimization. Simulated transactions can include think time to better reflect the timing of a real user taking an action, e.g., pressing the send button. The transaction response time plus the think time equals the elapsed time for that transaction. The transaction responses times collected during the performance test show how this measurement changes under different loads imposed on the system. Analysis may show no degradation under load, while other measurements may show severe degradation. By ramping up load and measuring the underlying transaction times, it is possible to correlate the cause of degradation with the response times of one or more transactions. Transactions can also be nested so that individual and aggregate activities can be measured. This can be helpful, for example, when understanding the performance efficiency of an online ordering system. The tester may want to measure the discrete steps in the order process, e.g., search for item, add item to cart, pay for item, confirm order, as well as the order process as a whole. By nesting transactions, both sets of information can be gathered in one test. 4.2.3 Identifying operational profiles. Operational profiles specify distinct patterns of interaction with an application, such as from users or other system components. Multiple operational profiles may be specified for a given application. They may be combined to create a desired load profile for achieving particular performance test objectives. See section 4.2.4. The following principal steps for identifying operational profiles are described in this section. 1. Identify the data to be gathered. 2. Gather the data using one or more sources. 3. Evaluate the data to construct the operational profiles. Identify data. Where users interact with the system under test, the following data is gathered or estimated in order to model their operational profiles, i.e., how they interact with the system. Different types of user personas and their roles, e.g., standard user, registered member, administrator, user groups with specific privileges. Different generic tasks performed by those users or roles, e.g., browsing a website for information, searching a website for a particular product, performing role-specific activities. Note that these tasks are generally best modeled at a high level of abstraction, e.g., at the level of business processes or major user stories. Estimated numbers of users for each role or task per unit of time over a given time period. This information will also be useful for subsequently building load profiles. See section 4.2.4. Gather data. The data mentioned above can be gathered from a number of different sources. Conducting interviews or workshops with stakeholders such as product owners, sales managers, and potential end users. These discussions often reveal the principal operational profiles of users and provide answers to the fundamental question: who is this application intended for? Functional specifications and requirements, where available, are a valuable source of information about intended usage patterns, which can also help identify user types and their operational profiles. Where functional specifications are expressed as user stories, the standard format directly enables types of users to be identified, i.e., as a type of user, I want some capability so that some benefit. Similarly, UML, use case diagrams, and descriptions identify the actor for the use case. Evaluating usage data and metrics gained from similar applications may support identification of user types and provide some initial indications of the expected numbers of users. Access to automatically monitor data, e.g., from a webmaster's administration tool, is recommended. This will include monitoring logs and data taken from usage of the current operational system where an update to that system is planned. Monitoring the behavior of users when performing predefined tasks with the application may give insights into the types of operational profiles to be modeled for performance testing. Coordinating this task with any planned usability test, especially if a usability lab is available, is recommended. Construct operational profiles. The following steps are followed for identifying and constructing operational profiles for users. A top-down approach is taken. Relatively simple broad operational profiles are initially created and only broken down further if this is needed to achieve performance test objectives. See section 4.1.1. Particular user profiles may be singled out as relevant for performance testing if they involve tasks which are executed frequently, require critical high-risk or frequent transactions between different system components, or potentially demand large volumes of data to be transferred. Operational profiles are reviewed and refined with the principal stakeholders before being used for the creation of load profiles. See section 4.2.4. The system under test is not always subjected to loads imposed by the user. Operational profiles may also be required for performance testing of the following types of system. Please note this list is not exhaustive. Offline batch processing systems. The focus here lies principally on the throughput of the batch processing system, see section 4.2.5, and its ability to complete within a given time period. Operational profiles focus on the types of processing which are demanded of the batch processes. For example, the operational profiles for a stock trading system, which typically includes online and batch-based transaction processing, may include those relating to payment transactions, verifying credentials, and checking compliance of legal conditions for particular types of stock transactions. Each of these operational profiles would result in different paths being taken through the overall batch process for a stock. The steps outlined above for identifying the operational profiles of online user-based systems can also be applied in the batch processing context. Systems of systems. Components within a multi-system environment respond to different types of input from other systems or components. Depending on the nature of the system under test, this may require modeling of several different operational profiles to effectively represent the types of input provided by those supplier systems. This may involve detailed analysis, e.g., of buffers and queues, together with the system architects and based on system and interface specifications. 4.2.4 Creating load profiles. A load profile specifies the activity which a component or system being tested may experience in production. It consists of a designated number of instances that will perform the actions of predefined operational profiles over a specified time period. Where the instances are users, the term virtual users is commonly applied. The principal information required to create a realistic and repeatable load profile is the performance testing objective, e.g., to evaluate system behavior under stress loads. Operational profiles which accurately represent individual usage patterns, see section 4.2.3. Known throughput and concurrency issues, see section 4.2.5. The quantity and time distribution with which the operational profiles are to be executed such that the SUT experiences the desired load. Typical examples are ramp-ups, steadily increasing load, e.g. add one virtual user per minute. Ramp downs, steadily decreasing load. Steps, instantaneous changes in load, e.g. add 100 virtual users every 5 minutes. Predefined distributions, e.g. volume mimics daily or seasonal business cycles. The following example shows the construction of a load profile with the objective of generating stress conditions at or above the expected maximum for a system to handle. For the system under test. Diagram 1. Example of constructing a stress load profile. At the top of the diagram, a load profile is shown which consists of a step input of 100 virtual users. These users perform the activities defined by Operation Profile 1 over the entire duration of the test. This is typical of many performance load profiles that represent a background load. The middle diagram shows a load profile that consists of a ramp-up to 220 virtual users that is maintained for 2 hours before ramping down. Each virtual user performs activities defined in Operational Profile 2. The lower diagram shows the load profile that results from the combination of the two described above. The system under test is subjected to a 3-hour period of stress. For further examples, refer to Bath. 4.2.5 4.2.5 Analyzing throughput and concurrency. It is important to understand different aspects of workload, throughput and concurrency. To model operational and load profiles properly, both aspects should be taken into consideration. System throughput. System throughput is a measure of the number of transactions of a given type that the system processes in a unit of time. For example, the number of orders per hour or the number of HTTP requests per second. System throughput should be distinguished from network throughput, which is the amount of data moved over the network. Section 2.1. System throughput defines load on the system. Unfortunately, quite often the number of concurrent users is used to define the load for interactive systems instead of throughput. This is partially true because that number is often easier to find, and partially because it is the way load testing tools define load. Without defining operational profiles, what each user is doing and how intensely, which also is throughput for one user, the number of users is not a good measure of load. For example, if there are 500 users running short queries each minute, we have a throughput of 30,000 queries per hour. If the same 500 users are running the same queries, but one per hour, the throughput is 500 queries per hour. So, there are the same 500 users, but a 60x difference between loads and at least a 60x difference in the hardware requirements for the system. Workload modeling is usually done by considering the number of virtual users, execution threads, and the think time, delays between user actions. However, system throughput is also defined by processing time, and that time may increase as load increases. System throughput equals number of virtual users over processing time plus think time. So, when the processing time increases, throughput may significantly decrease even if everything else stays the same. System throughput is an important aspect when testing batch processing systems. In this case, the throughput is typically measured according to the number of transactions that can be accomplished within a given time frame, e.g., a nightly batch processing window. Concurrency. Concurrency is a measure of the number of simultaneous or parallel threads of execution. For interactive systems, it may be a number of simultaneous parallel users. Concurrency is usually modeled in load testing tools by setting the number of virtual users. Concurrency is an important measure. It represents the number of parallel sessions, each of which may use its own resources. Even if throughput is the same, the amount of resources used may differ depending on concurrency. Typical test setups are closed systems, from the queuing theory point of view, where the number of users in the system is set, fixed population. If all users are waiting for the system's response in a closed system, no new users can arrive. Many public systems are open systems. New users are arriving all the time, even if all the current users are waiting for the system's response. 4.2.6 Basic structure of a performance test script. A performance test script should simulate a user or component activity that contributes to the load on the system under test, which may be the whole system or one of its components. It initiates requests to the server in a proper order and at a given pace. The best way to create performance test scripts depends on the load generation approach used. See section 4.1. The traditional way is to record communication between the client and the system or component on the protocol level and then play it back after the script has been parameterized and documented. The parameterization results in a scalable and maintainable script, but the task of parameterization may be time-consuming. Recording at the GUI level typically involves capturing GUI actions of a single client with a test execution tool and running that script with the load generation tool to represent multiple clients. Programming may be done using protocol requests, e.g. HTTP requests, GUI actions, or API calls. In the case of programming scripts, the exact sequence of requests sent to and received from the real system must be determined, which may be not trivial. Usually, a script is one or several sections of code written in a generic programming language with some extensions or in a specialized language, or an object which may be presented to a user by the tool in a GUI. In both cases, the script will include server requests creating load, e.g. HTTP requests, and some programming logic around them specifying how exactly these requests would be invoked, e.g. in what order, at what moment, with what parameters, what should be checked. The more sophisticated the logic, the more need for using powerful programming languages. Overall structure. Often the script has an initialization section, where everything gets prepared for the main part, main sections that may be executed multiple times, and a cleanup section where necessary steps are taken to finish the test properly. Data collection. To collect response times, timers should be added to the script to measure how long a request or a combination of requests takes. The timed request should match a meaningful unit of logical work, for example, a business transaction for adding an item to an order or submitting an order. It is important to understand what exactly is measured. In the case of protocol-level scripts, it is server and network response time only, while GUI scripts measure end-to-end time, although what exactly is measured depends on the technology used. Result verification and error handling. An important part of the script is result verification and error handling. Even in the best load testing tools, default error handling tends to be minimal, such as checking the HTTP request return code. So, it is recommended to add additional checks to verify what the requests actually return. Also, if any cleanup is required in case of an error, it likely will need to be implemented manually. A good practice is to verify that the script is doing what it's supposed to do using indirect methods, for example, checking the database to verify that the proper information was added. Scripts may include other logic specifying rules concerning when and how server requests will be made. One example is setting synchronization points, which is done by specifying that the script should wait for an event at that point before proceeding. The synchronization points may be used to ensure that a specific action is invoked concurrently or to coordinate work between several scripts. Performance testing scripts are software, so creating a performance testing script is a software development activity. It should include quality assurance and tests to verify that the script works as expected with the whole range of input data. 4.2.7 Implementing performance test scripts. Performance test scripts are implemented based on the PTP and the load profiles. While technical details of implementation will differ depending on the approach and tools used, the overall process remains the same. A performance script is created using an integrated development environment (IDE) or script editor to simulate a user or component behavior. Usually, the script is created to simulate a specific operational profile, although it is often possible to combine several operational profiles in one script with conditional statements. As the sequence of requests is determined, the script may be recorded or programmed depending on the approach. Recording usually ensures that it exactly simulates the real system, while programming relies on knowledge of the proper request sequence. If recording on the protocol level is used, an essential step after recording in most cases is replacing all recorded internal identifiers that define context. These identifiers must be made into variables that can be changed between runs with appropriate values that are extracted from the request responses, e.g., a user identifier that is acquired at login and must be supplied for all subsequent transactions. This is a part of script parameterization, sometimes referred to as correlation. In that context, the word correlation has a different meaning than when used in statistics, where it means relationship between two or more things. Advanced load testing tools may do some correlation automatically, so it may be transparent in some cases, but in more complex cases, manual correlation or adding new correlation rules may be required. Incorrect correlation or lack of correlation is the main reason why recorded scripts fail to play back. Running multiple virtual users with the same username and accessing the same set of data, as usually happens during playback of a recorded script without any further modification beyond necessary correlation, is an easy way to get misleading results. The data could be completely cached, copied from disk to memory for faster access, and results would be much better than in production, where such data may be read from a disk. Using the same users and/or data can also cause concurrency issues, e.g., if data is locked when a user is updating it. And results would be much worse than in production, as the software would wait for the lock to free before the next user could lock the data for update. So, scripts and test harnesses should be parameterized, i.e., fixed or recorded data should be replaced with values from a list of possible choices, so that each virtual user uses a proper set of data. The term proper here means different enough to avoid problems with caching and concurrency, which is specific for the system, data, and test requirements. This further parameterization depends on the data in the system and the way the system works with this data. So, it usually is done manually, although many tools provide assistance here. There are cases where some data must be parameterized for the test to work more than once. For example, when an order is created and the order name must be unique. Unless the order's name is parameterized, the test will fail as soon as it tries to create an order with an existing recorded name. To match operational profiles, think times should be inserted and/or adjusted, if recorded, to generate a proper number of requests or throughput as discussed in section 4.2.5. When scripts for separate operational profiles are created, they are combined into a scenario implementing the whole load profile. The load profile controls how many virtual users are started using each script, when and with what parameters. The exact implementation details depend on the specific load testing tool or harness. 4.2.8 Preparing for performance test execution. The main activities for preparing to execute the performance tests include setting up the system under test, deploying the environment, setting up the load generation and monitoring tools, and making sure that all the necessary information will be collected. It is important to ensure the test environment is as close to the production environment as possible. If this is not possible, then there must be a clear understanding of the differences and how the test results will be projected on the production environment. Ideally, the true production environment and data would be used, but testing in a scaled-down environment still may help mitigate a number of performance risks. It is important to remember that performance is a non-linear function of the environment. So, the further the environment is from production standard, the more difficult it becomes to make accurate projections for production performance. The lack of reliability of the projections and the increased risk level grow as the test system looks less like production. The most important parts of the test environment are data, hardware and software configuration, and network configuration. The size and structure of the data could affect load test results dramatically. Using a small sample set of data or a sample set with a different data complexity for performance test can give misleading results, particularly when the production system will use a large set of data. It is difficult to predict how much the data size affects performance before real testing is performed. The closer the test data is to the production data in size and structure, the more reliable the test results will be. If data is generated or altered during the test, it may be necessary to restore the original data before the next test cycle to ensure that the system is in the proper state. If some parts of the system or some of the data is unavailable for performance tests for whatever reason, a workaround should be implemented. For example, a stub may be implemented to replace and emulate a third-party component responsible for credit card processing. That process is often referred to as service virtualization, and there are special tools available to assist with that process. The use of such tools are highly recommended to isolate the system under test. There are many ways to deploy environments. For example, options may include using any of the following: traditional internal and external test labs, cloud as an environment using infrastructure as a service, IaaS, when some parts of the system or all of the system is deployed to the cloud. Cloud as an environment using software as a service, SaaS, when vendors provide the load testing service. Depending on the specific goals and the systems to test, one test environment may be preferred over another. For example, to test the effect of a performance improvement, performance optimization, using an isolated lab environment may be a better option to see even small variations introduced by the change. To load test the whole production environment end to end, to make sure the system will handle the load without any major issues, testing from the cloud or a service may be more appropriate. Note that this only works for SUTs that can be reached from a cloud. To minimize costs when performance testing is limited in time, creating a test environment in the cloud may be a more economical solution. Whatever approach to deployment is used, both hardware and software should be configured to meet the test objective and plan. If the environment matches production, it should be configured in the same way. However, if there are differences, the configuration may have to be adjusted to accommodate these differences. For example, if test machines have less physical memory than the production machines, software memory parameters such as Java heap size may need to be adjusted to avoid memory paging. Proper configuration or emulation of the network is important for global and mobile systems. For global systems, i.e., one which has users or processing distributed worldwide, one of approaches may be to be deployed load generators in places where users are located. For mobile systems, network emulation remains the most viable option due to the variances in the network types that can be used. Some load testing tools have built-in network emulation tools, and there are standalone tools for network emulation. The load generation tools should be properly deployed, and the monitoring tools should be configured to collect all necessary metrics for the test. The list of metrics depends on the test objectives, but it is recommended to collect at least basic metrics for all tests. See section 2.1.2. Depending on the load, specific tool, or load generation approach and machine configuration, more than one load generation machine may be needed. To verify the setup, machines involved in load generation should be monitored too. This will help avoid a situation where the load is not maintained properly because one of the load generators is running slowly. Depending on the setup and tools used, load testing tools need to be configured to create the appropriate load. For example, specific browser emulation parameters may be set, or IP spoofing simulating that each virtual user has a different IP address may be used. Before tests are executed, the environment and setup must be validated. This is usually done by conducting a controlled set of tests and verifying the outcome of the tests, as well as checking that the monitoring tools are tracking the important information. To verify that the test works as designed, A variety of techniques may be used, including log analysis and verifying database content. Preparing for the test includes checking that required information gets logged, the system is in the proper state, etc. For example, if the test changes the state of the system significantly, add or change information in database, it may be necessary to return the system to the original state before repeating the test. 4.3 Execution. Performance test execution involves generation of a load against the SUT according to a load profile, usually implemented by performance testing scripts invoked according to a given scenario. Monitoring all parts of the environment and collecting and keeping all results and information related to the test. Usually, advanced load testing tools or harnesses perform these tasks automatically, after, of course, proper configuration. They generally provide a console to enable performance data to be monitored during the test and permit necessary adjustments to be made. See section 5.1. However, depending on the tool used, the SUT and the specific tests being executed, some manual steps may be needed. Performance tests are usually focused on a steady state of the system, i.e., when the system's behavior is stable. For example, when all simulated users or threads are initiated and are performing work as designed. When the load is changing, for example, when new users are added, the system's behavior is changing and it becomes more difficult to monitor and analyze test results. The stage of getting to the ready state is often referred to as the ramp-up, and the stage of finishing the test is often referred to as the ramp-down. It is sometimes important to test transient states when the system's behavior is changing. This may apply, for example, to the concurrent logging of a large number of users or spike tests. When testing transient states, it is important to understand the need for careful monitoring and analysis of the results, as some standard approaches, such as monitoring averages, may be very misleading. During the ramp-up, it is advisable to implement incremental load states to monitor the impact of the steadily increasing load on the system's response. This ensures that sufficient time is allocated for the ramp-up and that the system is able to handle the load. Once the steady state has been reached, it is a good practice to monitor that both the load and the system's responses are stable and that random variations, which always exist, are not substantial. It is important to specify how failures should be handled to make sure that no system issues are introduced. For example, it may be important for the user to log out when a failure occurs to ensure that all resources associated with that user are released. If monitoring is built into the load testing tool and it's properly configured, it usually starts at the same time as the test execution. However, if standalone monitoring tools are used, monitoring should be started separately and the necessary information collected such that subsequent analysis can be carried out together with the test results. The same is true for log analysis. It is essential to time synchronize all tools used so that all information related to a specific test execution cycle can be located. Test execution is often monitored using the Performance Test Tools console and real-time log analysis to check for issues and errors in both the test and the SUT. This helps to avoid needlessly continuing with running large-scale tests, which might even impact other systems if things go wrong, e.g., if failure occur, components fail, or the generated loads are too low or high. These tests can be expensive to run, and it may be necessary to stop the test or make some on-the-fly adjustments to the performance test or the system configuration if the test deviates from the expected behavior. One technique for verifying load tests which are communicating directly on the protocol level is to run several GUI-level functional scripts or even to execute similar operational profiles manually in parallel to the running load test. This checks that response times reported during the test only differ from the response times measured manually at the GUI level by the time spent on the client side. In some cases, when running performance testing in an automated way, for example, as a part of continuous integration as discussed in section 3.4, checks must be done automatically, since manual monitoring and intervention may not be possible. In this case, the test setup should be able to recognize any deviations or problems and issue an alert, usually while properly completing the test. This approach is easier to implement for regression performance tests when the system's behavior is generally known, but may be more difficult with exploratory performance tests or large-scale expensive performance tests that may need adjustments to be made dynamically during the test. 4.4 Analyzing Results and Reporting. Section 4.1.2 discussed the various metrics in a performance test plan. Defining these upfront determines what must be measured for each test run. After completion of a test cycle, data should be collected for the defined metrics. When analyzing the data, it is first compared to the performance test objective. Once the behavior is understood, conclusions can be drawn which provide a meaningful summary report that includes recommended actions. These actions may include changing physical components, e.g., hardware, routers, changing software, e.g., optimizing applications and database calls, and altering the network, e.g., load balancing, routing. The following data is typically analyzed: comparing results to stated requirements, observing trends in results, statistical quality control techniques, identifying errors, comparing expected and actual results, comparing the results to prior test results, verifying proper functioning of components, e.g., servers, networks. Identifying correlation between metrics can help us understand at what point system performance begins to degrade. For example, what number of transactions per second were processed when the CPU reached 90% capacity and the system slowed. Analysis can help identify the root cause of the performance degradation or failure, which in turn will facilitate correction. Confirmation testing will help determine if the corrective action addressed the root cause. Reporting. Analysis results are consolidated and compared against the objectives stated in the performance test plan. These may be reported in the overall test status report together with other test results, or included in a dedicated report for performance testing. The level of detail reported should match the needs of the stakeholders. The recommendations based on these results typically address software release criteria, including target environment, or required performance improvements. A typical performance testing report may include executive summary. This section is completed once all performance testing has been done and all results have been analyzed and understood. The goal is to present concise and understandable conclusions, findings, and recommendations for management with the goal of an actionable outcome. Test results. Test results may include some or all of the following information: a summary providing an explanation and elaboration of the results, results of a baseline test that serves as a snapshot of system performance at a given time and forms the basis of comparison with subsequent tests. The results should include the date and time the test started, the concurrent user goal, the throughput measured, and key findings. Key findings may include overall error rate measured, response time, and average throughput. A high-level diagram showing any architectural components that could or did impact test objectives. A detailed analysis, tables and charts of the test results showing response times, transaction rates, error rates, and performance analysis. The analysis also includes a description of what was observed, such as at what point a stable application became unstable and the source of failures, e.g., web server, database server. Test logs, or information recorded. A log of each test run should be recorded. The log typically includes the following: date and time of test start, test duration, scripts used for test, including script mix if multiple scripts are used, and relevant script configuration data, test data files used by the test, name and location of data and log files created during test, HW, SW configuration tested, especially any changes between runs, average and peak CPU and RAM utilization on web and database servers, notes on achieved performance, defects identified. Recommendations. Recommendations resulting from the tests may include the following: technical changes recommended, such as reconfiguring hardware or software or network infrastructure. Areas identified for further analysis, e.g., analysis of web server logs to help identify root causes of issues and/or errors. Additional monitoring required of gateways, servers, and networks so that more detailed data can be obtained for measuring performance characteristics and trends, e.g., degradation. Chapter 4 ends.